The project title is Estimation of Position and Velocity using Kalman Filter, and I am the solo member of this project, Abdul Hanan. So, what is the problem statement? I am trying to predict position and velocity of a moving robot, and why is it a problem? Because let's discuss the scenario. So this is a robot on which I have a sensor installed, and I can very well measure its position and velocity. This sensor is IMU, initial measurement unit, which has a accelerometer and a gyroscope. And let's suppose gyroscope gives a linear velocity. And so I can, using this information, I can exactly know the velocity and position of the robot. But the problem is that the measurement noise from the sensor is always noisy, and I cannot completely rely on this sensor. The other way to know the position of this robot is by using a kinematic model of it. For example, I know the initial position and velocity of this robot. After some time, I can predict using the mathematical model where it would have moved and with what velocity if I know the input that have been applied to the robot. So in this scenario, I have considered input acceleration of 0.5 amplitude and sinusoidal. So with this acceleration, for example, this is the input. I can, with mathematical model, I can exactly know its position and velocity. Now, the problem using the mathematical model is that it doesn't know what is really happening. For example, the robot may have slipped on the surface. Therefore, I have to rely on the sensor data also. So this is where the Kalman filter comes in, that takes the measurement from the sensor and uses the mathematical model of this robot. It can get a better estimate of the position and velocity of the robot. So, for example, here in the green, in the upper graph, I have position, and the lower graph is the velocity. And the green graphs are the ideal position and the velocity are the true values, and in the red are the measurement from the sensor. As you see, the sensor is very noisy, but it is centered around the true value. So how would the Kalman filter get us a better estimate is in the brown box the Kalman filter is running. What it takes is a measurement from the sensor, which is basically the true value plus some measurement noise added into it, and it also using the dynamic model or mathematical model of the process, and the process noise, which is basically in our case can be there could be water present on the surface or slippery surface, etc. So that is the process noise, which is noise in the process itself. So using the Kalman filter, it can fuse the data of the measurement and this dynamic model and give a current estimate of the states and what is the uncertainty with that estimate, and also predict what will be the future state and uncertainty. So before implementing the Kalman filter, I have to model my system. This is the part of the modeling. So my state variable, the position and velocity, as I am interested in to estimate these two variables for my robot. And this is the system equation. So velocity is integration of acceleration, and position is the integration of velocity. So using this equation, I expand it using the time derivative, and in discrete form it converts to these two equations, and Yeah, then I go ahead to convert the state system equations into state space form, which becomes this form. And here, this is the first matrix is A and the second is B. So I have got system matrices A and B. Then H is the measurement matrix. So basically, 0, 1, 1 is because I get measurement of velocity from my sensor IMU, but I don't get any measurement of the position. So this is 0. Then the process now is covariance matrix Q, which is covariance in the measurement of in the process of position and in the velocity. These are assumed to be very small values. And then what is the measurement noise covariance matrix is basically what my sensor has the noise in it, and this is estimated from the data sheet. In the next slide I will show. And then covariance matrix, which is initially assumed to be identity matrix, as we don't know exactly what it is. Over time the Kalman filter will estimate it correctly and it will be updated. So how the matrix R is evaluated? So basically my sensor IMU data sheet says, which is MPU6050, it says that the noise spectral density is 0.005 per degree per second per square root hertz. So using this formula I convert it into variance, and then that is basically my R. This is how it was evaluated and put over here. And then now we have all the matrices as you can see here, and we can use them in our Kalman filter. Now these are the Kalman filter equations. So the first equation is basically process equation, which gives you estimates of the states, and the second equation is the measurement equation. So this is the recursive filter in which first we predict and then we correct our estimate. The first equation is basically F is basically A matrix and G is B matrix, which is related to the input, and with this we estimate our current state variables, and then we also estimate our uncertainty in our estimation of the state variables, which is B. And initially we give some initial state variable values and uncertainty, but over time it recursively evaluates these to be accurate. And so first of all you predict the state variable, then uncertainty, and in the second step it goes and then computes Kalman gain. And on the based upon Kalman gain, it estimates the state variable. So here the Kalman gain is basically a weighing coefficient which gives weights to measurement versus the process model. So this step is important in the sense that it gives priority or weighs what is more important, and based upon it, and then calculates the uncertainty, and then this is used in predicting the state variables again. Now so how it was implemented in the code, we have initially taken time in which the process is running, for example 10 seconds, and using the input which was defined as 0.5 sine. This is the true acceleration, and true velocity and position are estimated from this acceleration by using integration. This is the process of integration in this discrete time, and these are then used to compare with what Kalman filter estimates. So the sensor is modeled as for example the accelerometer as a 0.005 and gyroscope as 001 noise variance, which is standard deviation, which is basically given in the data sheet, and how the measurement acceleration is estimated like we have true acceleration calculated in the previous slide here, and then adding a random noise into it with the standard deviation mentioned in the datasheet. So measurement acceleration and measurement velocity is gained through this process, which will give me a noisy measurement, which models the sensor. And then this is the state space model of system which is used, A, B, H, Q, R, which were derived above, and then implementing the Kalman filter. And so as the acceleration is the input to the system, so this is equal to U, and then using the Kalman equations, we predict state variable, then covariance matrix, and finally I have estimated X, and then it is plotted over here. So this the first plot is noisy data versus true for the position and velocity, and this is like what sensor gives noisy data versus what the truth was, and the second graph is related to what Kalman gives estimation versus what the truth was, and it is plotted over here. So in the back you see the noisy data from the sensor in red color, green is the truth, and on the left side in this graph blue is the Kalman estimation, and as you see that it is very well aligned with the green curves. So it means that Kalman filter has estimated very well based on the sensor input and the process equations. That was it. Thank you. Any question?